So, good morning, everyone, or good afternoon, depending on where you are. So, it's a great pleasure to welcome you to this seminar within the Seventh Amazonian Symposium in Physics. And today we have the great pleasure to have with us Professor Luciano Rezzolla, Chair of Theoretical Astrophysics at the Institute for Theoretical Physics, Gotha University in Frankfurt. Thank you very much, Luciano, for being here with us. Professor Rezzolla is a leading figure in relativistic astrophysics, specializing in the physics of compact objects, black holes, neutron stars, as well as relativistic magneto-hydrodynamics and numerical relativity. Um, Notably, he co-led the Black Hole CAM project, which was an ERC synergy grant that contributed to the theoretical foundations for the first image of a supermassive black hole, M87 star. He also holds an ERC advanced grant for investigating the launching and propagation of relativistic jets. Luciano, I hope all this information is correct that I collected.
Yeah,
And
it is correct. Yes.
he is a co-author of the standard textbook Relativistic Hydrodynamics with Olindo Zanotti. He has published hundreds of peer-reviewed articles, received numerous awards, and in addition to that, Professor Rezzolla is an active science communicator. He published a general audience book, The Irresistible Attraction of Gravity, which was translated in multiple languages. And so, with that, I think that is enough to present Luciano. It's a great pleasure to have you here, and we look forward to your talk. So, please, the stage is yours.
Very good. Thank you, Carlos. Thank you, Crispino, for the invitation. And apologies for not being there with you in present. I am spending a sabbatical year at CERN, and this week just conflicts with a number of other commitments. And thank you, of course, Carlos, also for mentioning that about the outreach book. Yes. Unfortunately, the book has been translated in 10 languages, but Portuguese is not one of them. So if any of you in the audience knows a publisher is interested in Portuguese, in the Portuguese version of the book, uh, please let me know. So um, as Carlos has mentioned, I have, I normally work on things which are very down to earth, and I normally consider myself a very down to earth physicist. But this time I will present some ideas which are not are much more speculative, and in the last example would be really very almost science fiction. But I think this is the right audience. I know you work on exotic objects, and so I think this may be of interest to you. So the first topic I want to talk about are grava stars. And for those of you who are not familiar with this, let me just quickly remind you that they were introduced about 25 years ago by Mazur and Mazzola um, to produce a new solution for static spherically symmetric spacetime not in vacuum. Um, I remember when I first read this paper, I I was very happy because as a student I was told there is just one solution to answer the equation in vacuum, spherically symmetric and static spacetime, and that's a Schwarzschild black hole. And if you are not in vacuum, the equivalent is given by a self-gravitating star. Now, what Masur and Mortala propose is a third solution, a class of solution, which is exactly the Grava star. The interesting aspect of this is that a Grava star can be made arbitrarily close to the event horizon, therefore it can be indistinguishable, at least if you use electromagnetic probes. However, because these are really different objects and generativity is a unique theory, I mean, a theory that benefits from uniqueness results, um, it's not surprising that from a gravitational point of view, their response to gravitational perturbations, that is, quasi-normal modes, would be different. This is something that a Portuguese scientist Cecilia Chiarenti and I looked at many years ago. So, how do you get a gravastar? Well, it's here is the ingenious approach of Masur and Motola. You start and you patch two contrasting tendencies. Uh, the tendency of a de Sitter space-time to expand exponentially, and the tendency of matter-based space-time to collapse. And in this way, you can produce something that is actually in equilibrium. So space-time is really a patching of different space-times. You have a de Sitter interior, you have a matter shell, and you have a vacuum exterior. The Sitter interior goes up to a radial coordinate R1. The shell goes between R1 and R2. And of course, Schwarz is from R2 to infinity. Because this is a de Sitter interior, the equation of state is P minus E. In the vacuum where P equal E equals 0, and there is some equation of state, in particular P equal E in the original Gravastar model. This Gravastar model was having isotropic pressure, and this led to infinitesimally thin shells. But you can formulate this problem also in terms of thick shells with an isotropic pressure. In this case, the structure of the spacetime is something like this. Um, I think this is a much more realistic description because you can do not need to resort to infinitesimal shells, and you can have a much richer space of parameter because now the shell thickness will be a degree of freedom. So how do you solve this problem? Well, essentially you solve the Tolman-Penhamer-Volkoff equations for an isotropic matter fluid. You have to introduce a suitable equation of state for the matter shell, and these equations of state are, should in principle be based on some microphysical consideration, but in the case that we present, these are really unicorn matter, that is matter that we invent in order to have the mathematical properties that we like, that of continuity of the metric and fluid functions. And depending on how strict you want to be, you can have high order differentiability of these metric functions, or as in our case, top at second order. And so have functions which are continuous and with continuous first derivatives. These are the equations over here. Note that there is a tangential pressure which is added to the standard radial pressure. Well, the space of parameters, as I was mentioning, is not now a single point, but you have a space of parameter parameterized by the compactness delta and the thickness delta and the compactness, which is given by m over r2. R2 is the exterior of the gravastar. So there are two branches, as you can see here. There is this critical value of the compactness, of the thickness, and correspondingly compactness. And then there is a first branch. This is not a very interesting branch because these are gravas that have very thick shells, and also very small compactness. So these are, they will be looking not like compact objects. The most interesting is this part over here, which is where you can have thin shells and, asymptotically with delta equals 0, so infinitesimally thick shell, and compactness that reach 0.5. In particular, if we consider the solution over here in terms of the radial structure, so now I have compactness versus radial structure, and I have in blue the position of the inner part of the shell. You see that in this branch over here, R1 is at 0, and so you have essentially matter-filled objects, which are, pretty much what you would consider stars. And in fact, this is the Buchdahl limit. And then from the Buchdahl limit, you can produce objects that now have a finite but non-zero thickness. And eventually R1 moves outwards towards 2m minus. And in the limit, you have that R1 goes to m minus and R2 at 2m plus. And so you have the let's say the original Mazur-Motola um, model. So this was really just a recap of what Mazur and Motola did and an extension to have thick shells. Now, one first idea is to see a Grava star as an equilibrium between two behaviors. One, as I said, is the expanding the sitter, and the other one is the collapsing matter. And you can ask yourself, can we replicate this this structure? If you think for a second about doing this in the case of normal matter, you can't do this. Okay, you can't take a star and put on top another shell of matter, maybe a different equation state, and then on top another equation state, and so on and so forth. You will still be doomed by Bookdown limit. It doesn't care what equation state. So this definitely doesn't work for normal matter. But in the case of Gravastar, this is possible. And indeed, you can now split the spacetime in 5 different regions: 2 de Sitter shells, 2 matter shells, and 1 Schwarzschild vacuum. You have now more things to take into account. You see, this is the sitter interior. This is the second de Sitter interior between R2 and R3. The last shell is R3 and R4. You have equation state, which is the sitter, and then some matter, and then vacuum outside. So just more accounting, but nothing conceptually different. You can see here the structure, the radial structure. And again, what you want is to do what I've shown you in the first slides. Now you have to be a bit more careful because you have to ensure continuity of the metric and full function and first derivative at all the junction between 1 and 2, 2 and 3, 3 and 4, and then of course with vacuum. You can do this, it's not difficult. And this is just to give you an example that it is possible. On the left, you will see the radial structure of the metric function, so GRR and GTT. In blue, you see the de Sitter. In red, you see the matter shell. This is just one specific configuration, just to give you an idea. Interesting, and you can see that the metric function is perfectly smooth and continuous. You can see now the distribution of energy and pressure. In particular, you see that the energy is constant and equal to 1 for this choice of normalization E over E0. In the de Sitter, the corresponding pressure is negative, -1. You can see also that it has some smooth behavior, is not necessarily monotonic, doesn't have to be monotonic. And you see that the pressure, the tangential pressure, which is really the largest contribution, this number here has been divided by 15 so that I can show it in the same plot. So the bottom line is that these solutions are possible, are smooth, nothing dramatic happens. What about the space of solutions? Well, the space of solution now has 2 degrees of freedom. There's another degree of freedom, which is the thickness. You have 2 thicknesses because you have 2 shells. So you have delta 1 and delta 2, and you can calculate the space of solution again. Within the space of solution, which is delta 1, delta 2, you can show the compactness, which now is m over the last shell, R4. So this is a 2-dimensional space, but you can look at the most interesting sections, which are this one for delta 1 equals 0, and this one, which is for delta 2 equal to 0. Let me start from the first one. By the way, you can show that for compactness is larger than 1/3, you start producing light rings, inner light rings. So for delta 1 equals 0, you have pretty much the same picture I've shown you. It's not a surprise, okay? You are just replicating the Gravastar model that I was mentioning, okay? So I will not go in great detail here. More interesting is the branch for delta 2 equals 0, so where the second shell is infinitesimal. And in particular, I like this solution because, as you can see, R1 is always at R equals 0. So this is a de Sitter spacetime with 0 size. And R2, R3 and R4, they're all coinciding. So, down here, there is nothing very interesting, but up here with large compactness is in particular this object over here. This is the most interesting one because this is a solution where you have that the interior is essentially matter-based. And it's not fully matter-based because you still have a point of the sitter, and the surface is not made of matter, but it's made of this sandwich of the sitter matter. So strictly speaking, this is a violation of Bookdal theorem because you have an object which is much more compact than the limit, Bookdal limit, and is essentially all made of matter. Essentially is where the loophole is, because it's not entirely matter. You have that there is a very thin shell of the sitter. These objects are two nested gravastar, and because they are nested, we call them nestar. And this is therefore a new solution within full general relativity, how you can produce an object which is as compact as a black hole in particular. In this case I was mentioning, this would be, all made of matter. Of course, it's, funny matter, but it doesn't violate any condition. The strong condition is the only one that is violated. Now, you may ask at this point, why stop at 2? By the way, are you still on following me?
Yes, we are following you, Luciano.
Okay,
All
very
good.
good. So, because if you think the logic here is very basic, doesn't need to work just with 2. In fact, you can work with 3. And if you can work with 3, maybe you can work with k, an arbitrary number, integer. And in fact, that's what you end up concluding. All of what I presented here can be extrapolated to k shells. There are recurrence relations that allow you to write all of the expressions that I've shown you before for this case. So you would have 2k plus 1 regions, k of which are the sitter, k are made of matter, and of course the additional one is the Schwarzschild vacuum outside. The notation gets a little bit more heavy, but nothing dramatic. All you have to do is copy and paste what we've done for k equal to. So you can think that this is now a matryoshka of gravastars, where there is always one inside, and you can make this as compact as you want. I will now move to the next topic, which is the formation of a gravastar. Okay, what I'm showing you here is ChatGTP representation of a gravastar. I'm not sure where it got this from, but it's pretty cute, so I'm using it for this purpose. So, how do you produce a gravastar? I mean, I've told you how you can build a gravastar as a static solution. And yeah, I've shown you how you can build a gravastar as an S-star as a static solution. But how do you build a gravastar in the first place? Okay. Now, this is a problem that hasn't really been addressed. Okay, there have been a number of arguments made, first starting from Mazur and Motola, where they claim that quantum effects leading to trace anomalies of the energy momentum tensor could hold the collapse. Okay, so imagine that you have the collapse, and then as the collapse takes place, anomalies lead to additional thermal equations of motion, which would revert this. However, a fully dynamical system description has not been achieved. I should also mention that there have been attempts of collapse of massive shells, but again, a massive shell that then stops collapse. This is not quite what you would expect in nature. You would expect, a cloud of gas that at one point collapses. And in fact, the starting point is Oppenheimer-Snyder. That's the basic where a lot of our understanding on black hole formation, the singularity theorems come from. I'll just remind you that in space-time, this is a textbook um, representation. In fact, there is one in my textbook. You start with a homogeneous cloud of pressureless gas with initial surface Rs, and you can calculate everything analytically. This is because under this condition, the interior is just a Freeman-Lemaitre Robertson Walker space-time, and outside is a Schwarzschild. So you have that you can do this analytically. And what happens is that the surface reaches R equals 0 in a finite proper time, and this is the same proper time of all the other shells. There is no crossing of all the shells. All the shells will reach R equals 0 at the same time. At that point, you will produce a singularity because you have concentrated in a single point a finite amount of mass. So if you want to do this, if you want to produce a Grava star, you have to stop using this logic. Rather, you have to think that you want to start from the end. You have to have that you always have three spacetimes, a de Sitter, a matter spacetime, and a vacuum. And this is where the complications come in, because you have three spacetimes, you have three different coordinate systems that you have to take care of. You have matching conditions that you need to impose. And these junction conditions need to guarantee that the metric is continuous. And if you want, you can also have the extrinsic curvature is continuous. Well, this is something you can do, especially if you have a very patient and good student like Daniel. And that's what we've done. So for many, so we started from this configuration with three spacetimes, and we had lots of problems producing a Grava star. Only later on we understood why, but we couldn't quite produce a Grava star. We always ended up with something else, and let's say the breakthrough came when we decided to start from a Grava star and integrate back in time. In general relativity, you can do this, at least when a situation like this is time reversible. So that's what we did. We start from here, from the presence of a Grava star in a static space-time, and we integrate back to tau equals 0. And what you end up is word lines of this type. In particular, R1, the thick blue line, is the word line of the expanding de Sitter. Let me guide you through this plot. You start from an expanding de Sitter that initially has R as a proper radius R1 equals 0. This space-time then grows almost constant speed, and then, as you can see, accelerates and then decelerates. For those of you who are familiar with space-time diagrams, you see the deceleration because the slope of the word line tends to become vertical. In fact, is vertical in late times. So dynamically, you have to think that there is matter that is falling in, and then at the same time, there is a de Sitter interior which is expanding. But this expansion is nicely worked out in such a way that it stops expanding. It doesn't expand forever. It actually stops expanding exactly when it has to meet the infalling matter. You may ask, what happens to the matter that is intercepted by the expanding de Sitter surface? Well, this de Sitter surface has a large tangential pressure, so matter cannot penetrate it. And so the only thing it can do is it will have to be dragged along. Imagine this surface sweeping spherically symmetric manner, and the matter will accumulate at the edge. And as you can see in the inset, it will revert its motion, moving now to larger radii up until you end up here and you have an infinitesimal. Have all the matter, both the infalling and the outward moving, will concentrate it in a shell. Later on, we understood why we couldn't get the solution, and that's because in order to get the Grava star, so solution number two, you need proper initial conditions because you there are other possibility in this game. The first one is you actually the sitter inverts its motion, and that happens when the shell enters 2M, in which case you produce a black hole. The other possibility is that the intersection happens outside of 2M, and therefore you in this case you would have either a non-equilibrium or an expanding, a non-equilibrium in the terms of an expanding the sitter or something else. This will really depend on the conditions of what happens at point 3. So some tuning is needed in order to get number 2, but this tuning is not crazy. And that's because there is infinite sets of initial conditions that lead to case 2. What are these initial conditions? You have 2 degrees of freedom. One is the spatial curvature in the sitter region, what we call kappa 1, and the other one is the energy density in the sitter portion, which we call E1. So you have a 2-dimensional space, which is what I'll show you here. Okay. So in this space, K1, we normalize this to so that we have a number to kappa in the second region, and again, the energy density we normalize to the energy density in the matter region. Any choice of a K1 E1 on this red line will give you lead you a Grava star. Anything below will give you a black hole, and everything above will give you what we call a non-equilibrium. So again, for us, a Grava star is given by an asymptotic solution where R1 is a 2m and R2 is a 2m plus epsilon, where epsilon is set to be infinitesimally or as small as you want. It's an ODE. So, in our ODE, we set epsilon to be 10 to the minus 11, but you can set it to 10 to the minus 37 if you wish. I mean, it's just a matter of what you want to call small. Now, if you look at the spatial parameter, you see that there are 2 regions. One where E, the energy density, is small and kappa is large, and vice versa. One where kappa is small and E is large. This region intermediate, where kappa and E are intermediate, are the ones I've shown you. Okay, so you can think that the dynamics in this space of solution is actually different. Let me explain this a little bit better. So this is the space-time diagram, which I already commented. These are medium values of kappa 1 and E1. Already commented this figure. If you go on the other side, large K and small e, you obtain this situation over here, where you see that the expansion starts already rather quickly. If you compare the initial velocity here and the initial velocity here, this is much faster, and is almost constant up until the end, where the expansion breaks and then stops. Vice versa for small k and large e, the expansion is very bizarre and looks like so. The de Sitter bubble doesn't expand at all for a very long time. And only when you are close to 2m does the expansion take place. This is very, very fast. Don't forget, this is a de Sitter exponentially fast expansion. And again, this then is accelerated and breaks at R when the surface reaches 2m. I find this latter case the most interesting one. Okay, this one on the right. Why? Well, because this would be, essentially invoking standard physics that we know. The collapse could start very long time, and nothing would be different from what we know. Only later, when an event horizon is about to be formed, will the de Sitter be produced and lead to the Grava star. Also, because K is very small, you can think that this could be compatible with some quantum fluctuation of an almost flat space-time, which then leads to this bubble that expands. So it's a flat space-time but with a very large energy density. Again, you can think this is a quantum fluctuation of some time. As I said, these are very speculative considerations, so I will not try to defend this very hard, but it's an interesting possibility. Certainly, I find the rightmost more interesting than the previous one. And the last topic I want to cover, I'm already actually sorry for being. Do I have some more time, Carlos?
Of course, yes. I mean, you still have about 20 minutes if you want, if
Okay,
even
okay.
more.
Well, I I don't want to yeah. It was about 30 minutes for the. I was thinking 30 plus 10 of questions. Maybe I'll take um, uh, 5 or more minutes for this. So,
Sure. Okay.
can light rings self gravitate? This is a question that um, maybe may sound silly, but it is not so silly after all. Light rings play a fundamental role in the way we understand compact objects, in particular black holes. In the EHT work, everything is about a light ring. Okay, it's determining a shadow size and therefore getting to measure where the light ring goes, because as you know very well, this is a very strong signature of the space-time properties. And this is true not only when we're trying to use electromagnetic radiation to understand black holes, but also when we are using gravitational waves, because the black hole ring down again is fundamentally influenced by what happens at the um, at the tip of the at the maximum of the effective potential in the perturbative um, solution of the black hole solution. So no matter what you are doing, whether you're using gravitational waves or you're using light, light rings are the route to understand what you're dealing with. Okay. Okay. So in within this preamble, with Francesco Di Filippo and myself, we have asked ourselves this question: can you produce a self-gravitating light ring? Now, how do you produce a self-gravitating light ring in the first place? Okay, so this is where you need a bit of imagination. That's why it is called a Gedanken experiment. So imagine that there is an advanced civilization which has the ability to deposit an arbitrarily large number of photons on the light ring. Okay, this civilization is so advanced that can shoot a photon with the exact impact parameter that would allow it to fit onto the light ring. And now, because it is the exact impact parameter, it would stay there forever. Neglecting any other perturbation. Of course, whether this is possible or whether you have photon-photon interaction, non-linear photon-photon interaction that would change the property. That's something that is a higher order consideration, not the one I am making here. So I am assuming that once you shoot a photon with the right impact parameter, it will stay there. And if you can shoot a large number, then you are accumulating some amount of energy. And that means you can no longer treat a light ring as you would treat an effective potential of a geodesic particle. You have to resort to the Anson's equations, because at this point, light rings gravitate. And so the first question is, can a light ring self-gravitate? And if so, what are the consequences? So to answer this question, you need to, as I said, find a solution of the Anson's equation for a black hole surrounded by n null shells. And this problem, with n equal 1 is easy to find. And you can generalize what you know for n equal 1 to n. And if you look at the line element, it looks like so. You have this mn, and mn is just the the sum, the superposition of the mass of the black hole, the initial black hole mass and zero, plus the masses of all these shells that you are putting, each of which has a mass delta mi. They need not be the same. And now there are these other coefficients, psi n over here. Psi n are the coefficient that you need in order to guarantee continuity of the metric function. So in the simplest case, psi is equal, n is equal to, well, it would be equal to 0, and you would have Schwarzschild, and you can then easily extend from n equals 0 to n, well, I equal to 0 to I equal to n. So the solution can be found. You can calculate what is the effective potential in this new solution. So now it's the solution, the effective potential of a black hole plus a self-gravitating light ring. And this is what is really amazing, that the solution has a new light ring. Let me explain this with a plot. I think nothing is better than a figure. So this is the effective potential in Schwarzschild. There is what I define effective potential in this way. It's the ratio GTT over G5I. There are many other ways in which you can define it, but that's the way I define it here. And you can see this as a local maximum, and that's typical of an unstable circular photon orbit. Now, if you place matter on 3, and this matter now is self-gravitating, well, matter, I'm talking about light years. So if you build a self-gravitating light ring, the effective potential, the corresponding effective potential now will look like so. It's the new black line. And what is interesting is that the new black line has another extremum. And this extremum, therefore, is a new light ring. So the self-gravity of the first light ring has produced a new light ring, which is outside of the first one and will be at R1. Where it is, it depends on how much mass you put in the first light ring, okay? And now, because this is also an unstable circular photon orbit, the advanced civilization can decide to put more photons. And not only on the first one, actually the first one is full, and they start shooting photons on the second one. And for the solution I've shown you in the previous slide, what you find out that you can build now a new solution with 2 rings, and the 2 rings have now another light ring, which is again the location of an unstable circular photon orbit. So voila, you can repeat this game over and over, and you can build therefore now a new structure of objects which are in full generativity, where in the first object, the interior, the core is a black hole, and all the others are shells of matter, of null matter, of light. The position and the mass, so the position, if you want, will be depending on the mass, or the mass will decide where the new light rings will be. So you can construct this. You may ask, well, but this is requiring a fine tuning, and every time I have to fill in the next photon orbit. As a matter of fact, you can show that this is possible also in a continuum limit. That is where the shells of light, the light rings, if you wish, are all adjacent to each other. In this case, the junction conditional coefficients here are a bit more complicated, but a lot of magic happens in handling these analytic expressions, and you end up with something that is actually analytic. And the effective potential then looks like so, as given by this expression. There is an R in and R out, and the effective potential is constant between R in and R out. So it will look something like so. It's a flat potential between R in and R out, and you interpret this as a place of neutral stability. It's not unstable. It's not stable either. It's neutral stability. That means if you take a photon from here and you move it to a different radial position, it's still in a circular orbit. And so now we have produced a configuration, if you want, where you have a black hole at the center and you have a thick shell of light. And this is all within general relativity. I'm not invoking any complex non-Hilbert Einstein action. So the first question we have answered, yes, light rings can self-gravitate. Are they stable? Okay. Now it takes really, really easy to conclude that it is not stable. Let me go back to this one over here. Okay. So we built a situation where we have two light rings with matter. Is this configuration stable? You can easily imagine that it is not, because if the civilization doesn't get its aim right and sends a photon not on the light ring but into the black hole, then the black hole will change its mass, which means that this ring now will no longer be on an unstable circular orbit, and so the outer ring also. And so you can imagine this is like a, a castle of cards, an house of cards whereby a single photon is sufficient to destroy it. And this is true also in this configuration over here. The position of R in depends on the mass of the black hole, as you can see from here, and the size. If you now change M0 by adding an infinitesimal amount of mass, you change the potential. Analytically, you can show this very easily. The new potential will be the previous one plus a delta M, and the derivative of this potential will be positive. So instead of having a neutral stability, you will have that the top of the potential is now inclined, and this means that photons will no longer be on neutral stable orbits, but will be forced to either disperse or go into the black hole. So the answer is no. You can produce them, but they are unstable. Nevertheless, this is something that the civilization may find amusing, because they could think of building this shell of light and then destroy it by a single photon and see a big fireworks, because you can imagine all of the light that you have accumulated there will be dispersed very, very rapidly. Okay, let me come to the conclusions. I think both when you look at electromagnetic and gravitational wave observations, black hole general relativity provides a very good explanation for what we see. If you are a minimalist gravitational physicist, you can stop here. There is nothing more for you to do. However, most likely none of us in this audience is a minimalist, and we like to think about different options beyond general relativity, or within general relativity beyond black holes. I've shown you how a de Sitter can be used to produce a static configuration, and Nestor are a good example. Maybe there are more. I find it personally very compelling that every time you try to stop a black hole from forming, or better, every time you're trying to stop a singularity from forming, you need a de Sitter. This is what appears naturally in these bouncing solutions. So somehow this solution, the de Sitter solution, can be a natural cure within general relativity of the singularity problem. I've shown you that a gamma star can be formed from rather generic and realistic conditions. Well, I wouldn't call them realistic, but let's say not completely unrealistic. There is some tuning that is needed, but it is not an ultra fine tuning, because you have infinite options to play around. And if you do the tuning badly, you probably end up with a black hole or something else, or a de Sitter. And last, in my presentation, I've discussed about light rings, how they can self-gravitate and produce more light rings. this structure is unstable, but there is maybe some more interesting phenomenology. I know that a lot of the participants are young people, so this is really meant for you guys to find out and work out. There is essentially zero literature on esters. There is a lot of interesting things that can be looked at as stability. And the example of the self-gravity of the light rings is an example whereby, with a bit of imagination, you can come up with never found before solutions. And I think I'll stop here. Thank you.
Thank you very much, Luciano. So I think this was a sample of the applause that's going on
Okay.
in the auditorium. Thank you for this very thought-provoking seminar. Before we go into the questions, let me just tell you that we had about 50 people, 50 participating online, plus about 40 people in the auditorium. And online, we had people from various places, various Brazilian states, from Europe as well, from Portugal, from Italy, and from Brazil, from various regions, from the Amazonian region, the northeast, the southeast, and the south. So a good geographic sampling of the Brazilian community as well. Um,
Fantastic.
okay, and then there's a few questions already from the online participants. I think that we can start with a question by Albert Petrov, whom I can see already online. Albert is from João Pessoa in Paraíba. And Albert, please ask your
Yeah.
question.
Well, my question will be the following, perhaps a bit ingenious. Yeah. Can the gravastars rotate? Why I'm asking because we consider gravastar as some attempt to regularize black holes. We know that there are rotating black holes. In principle, we can construct rotating regular black holes. So whether we can introduce rotating gravastar.
So the answer is yes. People already, early on looked at this. There are, just like in the case of stars, you can work in what is called a slow rotation approximation. So where you start from a non-rotating and you add rotation as a perturbation, and you can find solution also in that case. Um, the I'm not an expert. Uh, I know that there are instabilities that appear when you have rotating gravastar. These are very generic instabilities that appear every time there is an ergo region. But I think there is a lot more that can be done there. I don't think um, it's obvious that all rotating gravastars are ergo region unstable. So, yeah, there are rotating gravastars, and some of them are not unstable.
Okay, so thank you very much. Just a little follow-up on that, since you mentioned the ergo regions. So would any rotating gravastar have an ergo region? Because in some of these objects, like say
No,
boson
so
stars.
this is a long. I've looked at this, but this was a long ago with Cecilia, and I don't think all of them have an ergo region.
Okay, that's what happens,
And I
say,
think
for
this is
boson
what
stars.
saves them, essentially.
Okay, so then let's move on to the next question. So we have a question from Nicolas Diaguiar Alves, and he didn't want to ask the question himself because he's on the phone. He's a PhD candidate at the Federal University of ABC, that's in Santo André, São Paulo. And the question, which I'm just going to read, is the following. Wouldn't the first massive light ring back react on the space-time and destroy itself because it changed the Schwarzschild solution, even if the photons are precisely at 3 m?
Well, that's the point. The solution doesn't is not destroyed. That's a static solution. That's a solution of the Einstein's equation. So if you think about the way you normally study the location of a photon ring, then you're assuming that you have a black hole space-time, Schwarzschild, say, and you have a test particle from which you solve the geodesic equation. But here, if you actually, maybe Luis can mute.
Yeah, there's some. Ah, okay, I think that's
Oh,
off.
okay. Um, this solution is a perfectly consistent solution of the Ansatz equation. So it's not a black hole anymore. Okay, it's not a Schwarzschild solution. It's a solution where you have a black hole plus a light ring.
All right. There's a third question online by Caio César Rodrigues Evangelista. I cannot see the affiliation, but oh yes, he's from Fortaleza, Ceará. So I'm not sure he wants to ask the question himself, so I'll ask it. The question is, what is the limit for the shells on the Nestor scenario? Do we just build as many shells as we want?
Yes, in principle, you can build as many as you want. We have built and studied two. Okay, so because it's easy to study the space of parameters, but in principle, one can study three, four. The formalism is fully generic, and that is why I think it's an opportunity for anyone who wants is interested in nestars to understand what is a space of parameters in the case of three nesters. Let me just go back here. Can you see my screen?
Yes, yes, we can.
Yeah. So you see, um, in this case, we found this new space of parameter with delta 2 equal to 0, which is this one. I have no idea what happens if you have now a delta 3. Maybe there is another interesting structure, and one can find, internal structures which are, more interesting than this one. So the bottom line is that um, there is a lot that can be done. We just didn't have enough stamina to do it.
Of course. Okay, very good. So I think that online there are no more questions. So I will turn now to the auditorium and
There
ask
is
if
another. There is a actor who.
Hector. Yes, Hector raised his hand just now. So Hector, you can go ahead and ask your question.
Hi. Well, first of all, thank you very much for all of these interesting ideas. My question is well, I was especially interested by the talk on this formation of gravastars. So I was wondering, do you expect to see any signature that can be observable of this expansion of the Sitter core that maybe could change the structure of shocks in supernova or something like this? Because that would be very interesting. No, it would be a proof that really something is going on that maybe we really don't have black holes, but gravastars.
Yeah. So thank you. Actually, this is of course a very important question. I think what I've shown you is for a pressureless gas. I think what happens here. Sorry, what happens here at the interaction between the expanding shell and matter when you have a real fluid, not dust, that's far more interesting because in principle you will create a shock, and this shock maybe will could even produce an expansion and break apart the infalling star. So yeah, maybe you could have something that looks like a supernova. um, from a gravitational point of view, even this configuration would have a different bring down signal than if you would produce a black hole. So I think, yes, in principle, there are observables that one can compute and come up with about how this would look like. And I think, um, the studying what happens in the interaction of the expanding shell with the infalling matter, that's a classical problem that we know how to solve because it's we see this in supernova.
Right. Well, thank you. I have another question, but maybe I should also give space for other people to ask.
Okay, Hector. So we can come back to you in a little bit. Let's
Right.
Actually, if I may ask a question related to the gravastar formation scenario, so how do you envisage it in a bit more detail? Because here there's a sort of initial condition, which is you have the center core expanding and the infall of this shell of matter. But I mean, is there a relation? That is the inner core, the center core expansion triggered by the matter, or would you have spontaneously cores, kind of bubbles of the center expanding? And as a kind of related question, what would be the magnitude in terms of physical values of the cosmological constant in this core as compared to, of course, it should be much, I guess, larger than present values that we use in cosmology. But how big would it be, and how much bigger, say, than the current estimates for the cosmological constant causing acceleration in a scenario where you have a cosmological constant?
So those were a lot of questions, Carlos. But
Sorry, sorry, sorry. Okay, please go ahead.
let me maybe give you an answer as a pure mathematical answer. You think the dot as an attractor in a space of ODEs solutions. Okay, all of the ODEs with different initial conditions, well, with the same initial conditions, the position of R2 and R1 will end up in this attractor position. And you will have an infinite number of different solutions um, with the same initial conditions. And these are the ones that are coming from this space of solution over here, okay? Small e and large k and vice versa. Now, what is it? This is really the mathematics of this. How you put this into a physical framework? Well, this is where I start hand waving arguments because I don't have a physical picture here. I'm just trying to give you a solution of a mathematical set of equations. But this one is not so crazy, I think, because you can think that there is a de Sitter of zero size for most of the time, and then something which could be chance, could be instead a la Masura Motola, some trace anomaly that triggers it, leads to the filling of this bubble with some energy density, and this energy density is then large, so that it leads to a very rapid expansion. And as I said, I think this is very hand waving, and I don't have a well prepared answer for this. The final answer is about what is the energy density. This has to be a huge energy density, okay, much larger than the cosmological constant, because you want this de Sitter to actually contrast the collapse. Okay, so in terms of energy, it has to have that amount of energy. The energy, the cosmological constant, in my understanding, it is very, very dilute. You see just on very large scales, and not on local scales.
Okay, thank you very much. Yes, I think that, yeah, there's a lot more to discuss here, but let's keep it that to another occasion. Uh, so I will go to the auditorium to see if there's any question that people would like to ask there. I see no reaction. Hello?
Can you hear me?
Yes.
Yes, great. It's Haroldo here. Uh, so thank you, Professor Rezzolla, for the very interesting talk. I have a curiosity about these compact object generated by the back reacting light rings. Uh, how is the gravitational lensing in this scenario? So imagine that you take a laser, a light ray that does not back reacts on the geometry; it just propagates in this space time. So do you have studies about the gravitational lensing of this laser in this background?
Oh,
So
that's a
how
great
this
question,
would
and
appear, how this would looks like for an external, a faraway observer, for instance.
that's a very good question. I have no idea.
Because my curiosity is the form of the effective potential, because this has a plateau, right? You
Yeah.
have shown in your presentation where this is flat. So thinking intuitively as the force as the gradient minus the gradient of the potential. So since the potential is constant, then the light rays would propagate in a straight line in this region. So this is one curiosity.
I haven't thought about this, but the metric is analytic. So if you have a code that calculates images or
Mm.
then it's trivial.
So in the continuous limit, you have an analytic metric
In both cases, it's
in both
analytic.
cases, the discrete and the continuous. Oh, oh, nice, nice, great. Okay, okay, yeah. Okay. So thank you again
Yeah.
for the
Thank
talk
you for
and
the
for
nice
the
question.
answers.
Thank you very much. There was a slight echo, but I think we could manage still. There's another question there in the room, I can see.
Yes. Hello, I'm Gabriel. I'm a PhD student from here, Belém. And I have two quick questions. The first one is about the Gedanken experiment of the accumulation of energy in the light ring. And it sounded quite similar to Wheeler's concept of geons. And I would like to know what's the difference, if there is any difference, and so what is it? That's the first question.
Actually, I thought geons have to do with gravitational waves, but
Yeah, electromagnetic sources also, if I'm not mistaken.
so I'm afraid, Gabriela, I can't give an answer. I don't know the geons too well enough to know.
Okay. So, and the second question is about when you show the effective potential and the possibility of occurrence of multiple light rings, you stress that there is multiple maxima in the effective potential, and from where I was seeing, it looked like there was no in between minimum. And one would naturally expect that two maximas, well, there would be a minimum in between. But from the plots, it appeared that there is actually discrete bumps. So maybe that's it. So is there minimums in between the maximas?
No, it's a monotonic function. It's a so
Right.
you go from, I don't know if you can see my screen. Um,
Yes, yes, I can see.
yeah, I don't know if I can magnify my screen, but this
Mhm.
is what the potential looks like. Okay,
Right.
so it's
So
monotonic
some discrete
functions. You
bumps.
reach another maximum, and then you reach another maximum.
Right. So
There are no minima.
so for instance, if you consider such a space-time and consider scalar perturbations in the space-times, one would not expect, for instance, although multiple light rings are observable, one would not expect to find quasi-bound states and long-lived trapped modes, for instance. So this would some maybe some mechanism of differentiating this type of spacetimes of other spacetimes with multiple light rings.
Yeah, I haven't thought about this, but I'm glad you're thinking about it. Yes. Um, but I mean, the way I see this is, it's a composite effective potential. So you are
Hmm.
replacing a simple maximum with a more complex structure, which still has a maximum.
Yes. Yeah, so I would assume, but I'm not sure, that quasi-bound states do not appear in this situation, although multiple light rings would appear. So this maybe is some nice toy model for perturbation. So the study of scalar perturbations, maybe.
Maybe. I think, one could repeat this analysis I've done for a black hole in the case of a compact object which has a light ring. And I think that you would see something very similar, with the addition that every time a new light ring is produced, maybe then also an inner light ring is produced. I don't know. It's something for you to think about.
Yes, sure. Thank you, Professor.
Yeah.
Okay, thank you very much. So just to identify, perhaps mute now the sound in the room so that we don't hear the echo. Okay, thank you. So the questions in the room were from a former student of graduate program in Belém, now a professor in São Luís do Maranhão, Haroldo Júnior, Lima Júnior, and now also from a student from the graduate program in Belém, just for you to know. And of course, before we have Hector Olivares, who's now in Aveiro in Portugal. And I think with that, I mean, we've exhausted our time. You must be tired, Luciano, also because you've given a talk just before this one. So it's been a long day, I guess, for you. I would just like to thank you again very much for the seminar and the thought-provoking ideas. And we will continue with the symposium. And hopefully, in a future occasion, you can be here with us. That would be a great pleasure. So thank you very
If
much.
I may.
I want to
Ah,
come to Belém
of course, of course.
sooner or
Okay,
later.
so I
Please
don't know
do
if you
not
can
hesitate
hear
with
me.
words. Yes, of
Yeah,
course.
I mean, it's just to, I mean, thank Luciano once again. Has been very kind of you, I mean, to accept our invitation to speak online. Obviously, we wanted you to be here in presence, and it's our wish for the future, right? And we hope we can manage the things to have you here as soon as possible. And before we close, I'll thank also the chairman, Carlos Herrera, for the excellent job. And I would like the audience to give a round of applause to Professor Luciano Rezzolla for the excellent talk. So thank you very much. Thank you.
Yeah. Thank you. All right. I'll log off now. Bye bye.
Thank you. Take care. See you soon, Luciano. Bye bye.
See you.